Hello everyone, I am Mansi Mahindru from ABES Engineering College, Ghaziabad. In today's lecture, I'm going to start with another approach of finding minimum spanning tree, that is Prim's algorithm. So let's start with the session. In the today's video, we're going to cover what is Prim's algorithm, what are the various steps for finding minimum spanning tree using Prim's algorithm, and the Prim's algorithm, actual Prim's algorithm that you have to write if it is asked in your university exam. And after that, some examples, or you can say some numericals. And at last, we're going to start with the complexity analysis of Prim's algorithm. Now, let's start with the session. And yeah. So, firstly, we have to understand what is Prim's algorithm. So, as it is written over here, that Prim's algorithm is nothing, it's a greedy algorithm, and it starts with the empty spanning tree. Now, the difference between Kruskal algorithm and Prim's algorithm is just like in Kruskal algorithm, we used to traverse all the edges in the ascending order, but here we're going to traverse each vertex one by one, and correspondingly, we're going to traverse the adjacent edges. The difference is just like this only, and rest, the main target is to find the minimum spanning tree. So let's start with these are some steps of writing of solving Prim's algorithm numerical, but these steps will be more clear to you if we'll solve one numerical first. Then we'll read these steps one by one, so that if this question will come for theory in your university exam, you can solve it easily. So now let's start with the numerical first. Now, if this question will come in your university exam, firstly, what you have to do, you have to assign all the vertices as infinity. Means you will going to assign the key value to all the vertices as infinity, like this. After this, see, we cannot feed this particular graph in our memory. So we have to convert this particular graph in the form of weighted matrix. And in that particular weighted matrix, we have to maintain three things. Means the first thing we have to maintain is the track of all the vertices. Means, as I already told you in Prim's algorithm, we used to traverse each vertex one by one, and we're going to repeat the same process till all our vertex set will be equals to 0. So these are all the vertices that we have included in the graph. So I have added all the vertices here. Now, the second thing that we have to maintain is the key value. Means current key value we have assigned to each vertex. So as per our current scenario, I have assigned all the vertices as infinity. So I have written here infinity. Now this pi is nothing. It's basically the parent value. Now I haven't choose any vertices till now. So the parent value is currently nil. You can write nil, you can write n, whatever you want to write. So the parent value is nil. Now we have to start our journey from some point. If it is given in the question that you have to start your journey from this source vertex, then you can choose that. Otherwise, if in the question it is not given, then just choose the first vertex as your source vertex. So I will choose this as my source vertex, and I will update this source vertex in my weighted matrix also. So what I will do is I will going to reduce its value from infinity to 0, infinity to 0, and I will do this updation in my weighted matrix also. As you can see here, I have done this updation in my weighted matrix also. I have assigned A as 0, but currently A is not connected to any other vertex, so the parent value will be equals to nil. After this, I will going to check for the minimum key. So among all the vertices is in my weighted matrix, A is minimum because A key value is 0, and for rest of the vertices, it is infinity. So I will going to extract A from this weighted matrix. Like whatever extraction I will do now, I will going to store it in some variable, or I will take this variable as U. So this you will maintain the set of extracted vertices, right? So what I will do is I will going to extract A from this weighted matrix. Now I will going to visit A. So again, I have created one weighted matrix here, and here I will write that I am going to visit A vertex. So let's start our journey from A. From A, I can go to B, I can go to H. As we can see in the graph, from A, there is a direct edge going to B and to H. But whatever vertex you are visiting, their key values and their parent value will not get updated. It will be taken from previous weighted matrix. Just note this. This is very important step. So from the previous weighted matrix, it is saying that the key value of A should be 0 and the parent value should be nil. So I have copied it from the previous matrix. Now I will going to check for the adjacent vertices from A. So as it is written that from A, I can go to B and I can go to H. If I'll go to B, I will going to H, or I will going to add the weight 4 to B. Now B is currently holding value as infinity. And I can see this that 4 is less than infinity. So I can update this key value pair. So what I will do, I will going to update it to 4. So let's go to the weight matrix and do these updations on in weighted matrix also. So I will write here 4. Now the parent of B vertex will be A, right? Now from A, I can also go to H. And H is currently holding infinity and I am giving 8. So 8 is less than infinity. So I can update this. So this will be 8 and the parent is A. So do this in the graph also so that every step will be clear to you. So you will be holding it as 8. This will be 8. Now, from A, we cannot go to any other vertex. So rest of all the values will be copied from the previous weight matrix. Like it will be infinity, nil, infinity, nil, infinity, nil, infinity, nil, infinity, nil, and this will be again infinity and nil. Now, this rectangular box is saying that A is already visited. Now what we'll do, we're going to extract the second minimum key value. So as you can see here, this is 8. We have 4, infinity, 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 8 and infinity. So among all these vertices, 4 is minimum. So what I will do, I will going to extract B from this weighted matrix. Let me take different color pen. It will be easy for you to understand. Now I will going to extract B from this weighted matrix. And now let's do all these updations in new weighted matrix. Second. Yeah. So this is my new weighted matrix. And whatever I have done is, as per my previous weighted matrix, I have already visited A. And the node that is being already visited, their value, their parent will be copied from the previous matrix. So which is saying 0 and nil. And now I am going to visit B. So its value will also be get copied from the previous matrix. So it will be 4 and it will be A. Now for rest of the values we're going to check. Now as you can see from B, we can go to A, but this A vertex is already visited. So we will not visit it again. So we cannot go to B. From B, we can go to C. From B, we can go to C. And if we're going to visit C, we're going to add edge weight 8. And C is currently holding infinity. So our edge weight 8 is less than infinity. So we can update this value. So now in the weighted matrix, let's do this updation again. So what we will do here, we will going to write 8 and its parent will be B. From B, we can also go to H. Now, if we're going to go to H, we are adding H weight as 11, but H is holding 8, and 8 is less than infinity. So, we're not going to update that particular thing here. So, H will not be updated because we are giving 11 and H is already holding 8. So, why H will take our value? Because we are giving increased value, no? So it will not take because we are constructing minimum spanning tree. So we're not going to update that particular thing here. Let me take different pen again. So it will be more easy for you to understand. Yeah. So H will not get updated. H will be again 8 and A only. And from B, we can go to A, we can go to C, we can go to H. No other vertex we can traverse. So all the remaining vertex value will be copied from the previous matrix infinity, nil, infinity, nil, infinity, nil, infinity, nil, and this will be again infinity and nil. Now again, we're going to check for the minimum value. As you can see here, C key value is also 8. H key value is also 8. So we can choose anything. We can choose any one of them. But again, we're going to follow the stable sorting. Okay, we're going to follow the stable sorting. So whatever comes uh, first in the input will also be first in the output. So for this, what we will do, we're going to extract C. We're going to extract C from the weighted matrix. Now let's do all these updation in the new weighted matrix. So as per our previous weighted matrix, it is saying that you have already visited A. Second. Let me do all these updations again. Yeah. So from the previous matrix, it is saying you have already visited A and value is 0n. You have already visited B, value is 4A. And now you are visiting C, so its value will be 8 and B. Right? Now from C, we can go to D, and D is still untraversed. It is still untouched node, and we are giving 7, and D is currently holding infinity. So it can be updated. It can be updated because we are giving less weight to D, and D is already holding infinity. So it can be updated. So it will be 7, and we're going to change this thing also in our weighted matrix. So from C, we can add here 7 and parent will be C. From C, we can go to B, but B is already traversed, so we're not going to add this. From C, we can also go to I, and we are adding weight as 2, and I is holding infinity, so it will accept our value. So we're going to update it as 2. So its value will be infinity to 2. Let's do this updation in this weighted matrix also. And what we'll do in I, na? Yeah, in I will write 2 and its parent will be C. From C, we can go to D. From C, we can go to I and C. Yeah. From C, we can go to F also. From if we'll go to F, we are giving edge weight as infinity, and currently it is holding infinity, and we are giving edge weight as 4. So it will accept our value. Let's add this thing also. For F, it will accept our value. Let's update this thing. It will be 4. So let's do this updation here also. It will be 4 and parent will be C. From C, we can go to B, D, I, and F. No other vertexes left. So we'll copy it from the previous weighted matrix. So it will be infinity, nil, nil, infinity, nil, infinity, nil. Now again, we're going to check for the minimum. Now we find that I is minimum among all the vertices. So we're going to extract I. We're going to extract I. Now, when we're going to extract I, let's do all these updation in the weighted matrix also. And let's draw the weighted matrix again. And from the previous matrix, we got to know that these values already visited, this is already visited, this is already visited, and now we are visiting I. So let's mark this as visited. And again, we're going to copy all the previous values from the weighted matrix 0, nil, 4A, 8B, and for I, you're going to write 2C. Now from I can go to C, but C is already visited. From I can go to H, but H is still not visited, and I am going to give weight as 7, and H is holding as 8, so 7 is less than 8. We can update this. We can update it easily. So what we'll do, we're going to update it to 7, and at the place of H, we're going to write, but one second. Once again, it should be 8 and it should be A. Hmm. From in H place, what we will do is we're going to write 7 and its parent will be I. From I, we can also go to G, and the edge weight we are giving is 6, which is less than infinity, so it will accept it, and parent will be I. Let's do this particular updation in the graph. So it will be 6. Yeah. From I, we can only visit C, H, and G. So all updations are done. So let's update the previous value, all the remaining values from the previous matrix. So D will be 7C, E will be infinity nil, F will be 4C. Now let's extract the next minimum, that is F. So you will going to extract F from this weighted matrix. Again, we're going to extract, and let's do updation in the different weighted matrix. So according to this, A is already visited, B is already visited, C is already visited, I is already visited, and now we are visiting F. So all the values will be copied from the previous matrix. 0, nil, 4A, 8B, 4C, and I will be 2C. Now let's traverse F. From F, we can go to E. And E is still infinity, so it will accept our value as we are giving 10 and it is infinity. So it will accept, so it will write here 10 and the parent will be F. Yeah, parent will be F. Let's do updation in the graph also. Second. Yeah. So it will be 10. Now from F, we can go to D. D, we are giving 14 and it is already consisting of 7. So why it will accept our value? It will not accept, so no updation will be done. So it will be 7 and next is C. From F, we can go to C, which is already done. From F, we can go to G and we are giving 2 and G is currently holding 6. So it will accept our value. And so to G, we're going to do here, it will be, we are giving 2 and its parent will be F and this will be nothing, it will be 2. From 6 it will get reduced to 2. From F we can go to E, D, C and G. So we have done all the updation. From F we cannot go to H, so H value will not be copied. F value will not be updated, will be copied from the previous weight matrix. So it is done. Now again we're going to check for the next minimum and we are getting G. So what we'll do, you will going to extract G from this weighted matrix. Let's draw another weighted matrix here and let's take another pen so that you'll not get confused. Okay, so from the previous matrix, let's do all the updations again. From the previous matrix saying we have already visited A, value will be 0, nil. We have already visited B, value will be 4A. We have already visited C, value will be 8B, and we have already visited F, weight value will be 4C, and next is I, and that is 2C. Now we're going to visit G. Now we're going to visit G, so it will be 2F. Now let's start traversing G. If we'll traverse G, from G I can go to I. I is already visited, so we'll not do that. From G, we can go to H, and we are giving 1, and H is currently holding 7, so it will accept our value. Obviously, it will accept it. So 7 will get reduced to 1. So at H place, we'll write here 1, and parent will be G. From G, we can go to F. F is already visited, so we'll not go there. From G, we can only traverse I, H, and F. So we'll not do any other updation. From D, we cannot go, and I, we cannot go. Yeah. So from D and E, we'll copy it from previous matrix, 7, C, and next is 10, F. See, we are copying it from this particular matrix because this is our last updated matrix. So we'll copy it from here only. So again, you will going to extract the next minimum, and you will find that the next minimum will be H. Let's do all this updation in the weighted matrix. So next, from the previous matrix, it is saying that you have already visited A, value is 0 nil. You have already visited B, value is 4A. You have already visited C, value is 8B. You have already visited F, 4C. You have already visited G, value is 2F. You have already visited I, 2C. Now you're going to H, you're going to traverse H, value will be 1G. Okay, so from H, you can go, see, you cannot go to D and you cannot go to E. There is no direct H. So we're not going to do any updation. We're going to directly will copy the values from the above weighted matrix. We'll not do any updation because from H we cannot go anywhere. From H we can go to A, we can go to I, we can go to G, but all these vertices B, we can go to B also, but these vertices are also already visited, so we cannot visit them again. So do all updations like 7C, 10F. Yeah. Again, you will going to extract. So you will extract D. Let's construct one more weighted matrix here. And let's do all the updations again. A visited 0 nil. B visited 4A. C visited 8B. Okay. And now we are visiting D now. Yeah. So 7C. F already visited. 4C. G already visited. 2F. H already visited 1G, and I already visited 2C. Now we are visiting D. Now let's see D. From D, we have only one option left, that is E. And if we'll move to E, we are adding edge weight as 9, and E is holding 10. So yeah, it will accept our value. It will accept it. So we'll do that updation here. So we'll write here 9, and the parent will be D. Let's do this operation here also. So it will be 9. Yeah. Now next, we're going to extract next minimum, that is only E for sure. So you will extract E, but from E we have no option left to traverse. So we'll simply put it in the set. And now our visited node set is empty. Unvisited node set is empty. So we can stop here, and now we can draw the minimum spanning tree based on this particular weighted matrix. The last weighted matrix that we have created is our final matrix on which we're going to construct the minimum spanning tree. So to construct the minimum spanning tree, it's very simple theory you can follow, very simple approach you can follow. So what you have to do is you have to create the disjoint set first. Let's create the disjoint set. A, B. Just look at the question and just place it there only. C, D, then E, then this will be H, then this is G, this is F, and this is I. Yeah. So I have done this. Now just look at the last updated matrix which you have drawn. And you have to follow a sequence from parent to the value. As you can see here, initially A is connected to nil, means nil is connected to A. Matlab A is not connected to any other node, so just leave it like this only. Next, in next column, it is saying A is connected to B. So let's connect this. A is connected to B. Okay. It is saying that just connect your A with B and see edge weight will be same as you have assigned it in the question. So edge weight will be 4. Done. Next, it is saying that you have to connect B with C. If you are getting confused, just see this column. Just travel from here to here. B is connected to C. Let's connect this. B is connected to C and edge weight will be 8. In the next column, it is saying C is connected to D. C is connected to D. Let's connect this and edge weight will be 7. Next, it is saying D is connected to E. D is connected to E. Done. And edge weight will be 9. Next, it is saying C will be connected to F. C will be connected to F and edge weight will be 4. Next, it is saying F is connected to G. F is connected to G and H will be 2. G is connected to H. G is connected to H and edge weight will be 1. And C is connected to I. C is connected to I. And edge weight will be 2. So this is your minimum spanning tree. This is your minimum spanning tree. If anyone asks you to calculate the cost, just add 4 plus 8 plus 7 plus 9 plus 4 plus 2 plus 1 plus 2 and you'll get your minimum cost. So the minimum cost is nothing. It will be 37. So this is your question or this is your method by in which you have to solve your question. Like this you have to solve in your university exams. So now we can move to these steps. As you can see here, it is saying that you have to assign all the values to infinity. And after that, you have to pick the vertex which is not in the MST set and find the minimum key value. Include U to the MST set. So whatever we have done, the steps are written over here. If you want to write it or if you want to use it as your theory question, you can use it. So let's move to next thing. Yeah. So this is our algorithm. This is algorithm for Prim's. Now Prim's algorithm is also very simple. So in the Prim's algorithm, while doing the numerical, the first step we did is we have the first step is we're going to pass graph G, weighted matrix W, and R means our source vertex in the function. Now, when we started with our question, what we did is we have assigned all the values as, one second. Now, what we did, see, in while solving the numerical, the first thing we did is we have assigned all the values or all the vertices as infinity. So similarly, we are doing here. So what we'll do, we're going to take all the vertices and we're going to assign all the key values as infinity and their parent will be assigned to nil. After that, we have to start our journey from some point. So we're going to take one of our as a source vertex and we'll update its value to 0. Similarly, we have done in the numerical. After that, what we did is we have created the weighted matrix, and from that weighted matrix, we have extracted the minimum value. So for that, what we do is we're going to create one min heap, because the property or the beauty of min heap is that the smallest value will be present at the root node. So what we'll do is we'll create the min heap. So from this particular step, 0 will be on the top, means the scenario will be 0 will be this, means the source vertex will be at this position, and all other values or all other vertices will be like this. Their value will be infinity. But we can easily extract this minimum value from the root node. So in this particular point, we're going to create the min heap for all the vertices, and this while loop will run till the point this min heap will be empty. The point where this min heap will be empty will stop here. Now, after this, once we have extracted our first node, as we did in the question, we have extracted A because its value is 0. So what we did, we have stored it in some variable and we have stored it in U. After that, we have checked that from U or from that particular vertex, how many vertex we can traverse. So what we will do is, see, for each vertex V adjacent to U, we will going to check the weight that we are giving. Is it less than the key value it is already holding? If the weight that we are giving is less than the value it is currently holding, then we will going to update its parent and we'll going to update its value. This particular algorithm is designed in similar manner as we are doing the numerical. There is no difference. Whatever we have done in numerical is simply written over here. So you don't have to learn it. You have to only apply your numerical logic here and you have to write this algorithm. So this algorithm is very simple. Now, after that, we have to do the analysis. You have to find out how much time this algorithm will going to take to run. So let's do the complexity analysis one by one for each step. Okay. Yeah. So if we'll talk about this particular step, all the initializations that we are doing means we are initializing all the vertices as infinity and all the parents as nil. It will take O of V time because we are doing it for all the vertices. So definitely it will take for O of V time. After that, we are assigning our source vertex as 0. So it will take O of 1 time. After that, we are creating one heap. We are creating one heap of all the vertices so that the minimum value will be on the root node. So it will also take O of V time. Now, this while loop will run फॉर वी टाइम बिकॉज जब तक वो वर्टेक्स का पूरा सेट एम्प्टी नहीं हो जाता ये वाला वाइल लूप आपका चलता रहेगा. मतलब वो जो क्यू सेट था वो आपका जब तक एम्प्टी नहीं हो जाता तब तक आपका ये वाला लूप चलता रहेगा. तो दैट इज व्हाई इट विल टेक ओ ऑफ वी टाइम. आफ्टर दैट व्हाट वी विल डू, we will going to extract the minimum vertex from the weighted matrix, from the minimum heap, or you can say your min heap. So during the lecture series of binomial heap, we have already done this operation and we find out there that the min heap, or you can say extract min operation, takes log of n time. Log of n time. So let me take my pen. Let me take different pen. Yeah. So this particular step will take log of v time. But we will going to do this step for v time. As you can see, this extract min is a nested loop inside v. So this particular extract min will be called for v log v time. Yes. After that, once we have extracted our minimum vertex, then we have to look for all the adjacent vertices. All the adjacent vertices. So this vertices. Now, at this particular step, there are two possibilities. There are two possibility, means the graph can be dense and graph can be sparse. Now, if the graph is dense means the graph is complete. Now, as you can see, if the graph is complete, then all the vertices are directly connected to other vertices. So that means if we look about the adjacency here, so all the vertices are adjacent to every other vertex. So we can say that for the dense graph, this step will run to V minus 1 time. This step will run for V minus 1 time. And this particular thing is also inside this nested loop. So this step will run for V into V minus 1, which is what? V square time. Now, after this, inside this nested loop, there are three statements. Means whatever weighted value we are assigning to this vertex, whatever value we are offering, is it the value less than the value it is currently holding? We are checking this, right? So if this particular condition is true, then we are decreasing the value. And decrease key operation, we already know it will also take log of V time. It will also take log of V time. And this is also a nested loop inside this statement. So this particular step will take V square log V time. Now let's do the complete analysis. So for 1 to 3 step, we got O of V plus step 1, 4 takes O of 1 plus fifth step take O of V plus sixth step will take O of V, but this step will not execute alone. There are some nested statements as well. So seventh statement is nested inside sixth statement. So it will together it will take O of V log V plus. Now sixth and eighth step is again a nested loop. So it will take O of V square, and along with that 9, 10, 11 statement will also get executed. So V square log V. So the dominating term is O of V square log V. So it will be O of V square log V. But the constraint is that graph is dense or the graph is complete. But what if a graph is not dense? It is a sparse graph. It is a normal graph. Then in that case, we can say, just I'm right here. In that case, what we will take is E is equals to V square. We'll trade key on max to max. In worst case, it will go to E time. Means this particular statement adjacent for each vertex V belongs to adjacent of U will only take E time. So it will be O of E log V. So this is the time complexity of Prim. Sometimes in the gate question, they have written O of V square log V, and sometimes they will mention E log V. So don't get confused. They both are same, just the scenario is different. Sometimes they are talking about dense graph and sometimes they are talking about sparse graph. So this is all about the complexity analysis. We have already done this numerical. You can pause this video and you can solve these questions once again by yourself. And in this particular thing, I have already done complexity analysis, but I have also already showed this particular analysis with the help of pen so that it will be more clear to you. Okay, thank you for patient listening and do subscribe CETL channel. And in the upcoming lecture, we're going to start with single source shortest path. And that particular video also consists of two main approaches, that is Dijkastra algorithm and Bellman-Ford algorithm. So stay tuned for those videos. Thank you.